All right, now we're going to do questions 6 through 9 on day 3. Question 6 also gives us a piecewise function, very similar to the first one you did today. And it says that this is equal to this for anything not 2, and this is just k for 2. And we want to know, what does k have to be for this to be continuous? So in other words, the limit has to equal the actual function. So we can see right here that if we knock that out, f looks like 2x plus 1 for anything that's not 2. If I were to put 2 into that, that means it looks like it should equal 5. So if we were graphing it again, it would be coming in and look like it equals 5. Now, for this to be continuous, I can't have that hole there. So I need to be able to plug the hole by defining it to be that value. Therefore, k has to equal 5 in order for this to be continuous. Okay? So the top and the bottom have to equal at that spot in order for them to have that continuity. Okay? Not too bad. Hopefully you got that one. Next one's a little sneaky. It says, what's the limit as x goes to 0? So if you thought that that was infinity, you might have tried to do one of our, simplifying things and whatnot. But truth is, probably you can do L'Hopital's on here, because if you put 0 in, you get 0 over 0. It will take you 3 or 4 tries to get to the final answer, and that's fine. There is a little quicker way, and that is you could pull an x cubed out of the top here, and we'd have 2x to the third plus 6. And then you could pull an x cubed out of the bottom. You'd have 4x squared plus 3. Let those x cubes cancel. And now let's try the limit as x goes to 0 of what we have left over. And what's going to happen is these are going to 0 out, and you're going to be left with 6 divided by 3, which is 2. Right? So again, you got to be a little careful either way you go there, but not too bad. All right, the next one here gives us a function given by this. We want to know where we have a relative minimum. So kind of a straightforward problem. We know the first thing we got to do is find our critical points. So we take our derivative. We set it equal to 0. I'm going to pull a 6 out while I do it. And I'm going to have x minus 2, x plus 1, which gives me x equal to 2 or negative 1. Okay, so I could actually get rid of 3 choices right now, but in order to know for sure, I've got to test these, right? So I put negative 1, I put 2 down. I'm going to test 0 right away, so if I go back to my derivative and put 0 in, I'm going to get a negative there. If I put in something big, something like negative 10 in, I'm going to get 100, so 600 plus 60, so those are going to be positive values there. If I put in a positive 10, 600 minus 8, that's also positive. All right, relative minimum is when my derivative switches from negative to positive. My negative to positive switch occurred right there. So 2 is my answer. So hopefully you got that one. That's a oldie but goodie. Not too bad there. All right, then we get to the last one. The last one definitely was the hardest of these 4 here. It says for a certain function, the right-hand Riemann sum with n subintervals equals this. So they're saying that if you use 5 subintervals, put 5 in for n, and that would be your right-hand Riemann sum. If you use 10 subintervals, put 10 in, and that would be it. We want to know what is the actual value. And so, in other words, we don't want to just use 5 or 10 or 15 subintervals. Like when you're approximating, if you use a few, you get a okay approximation. I'm sorry, I'm being kind of quick here. My rectangles look silly. If you use a few rectangles, you leave some area behind. If we increase, the number, if we make them skinnier and use more of them, well, okay, we're getting a little better approximation, right? But if we want the actual value, then we need to use basically an infinite number of rectangles, right? So in other words, what happens if we let n go to infinity? What if we have the number of rectangles actually go to infinity here? That's what they were kind of getting at here. And again, that wasn't so obvious, but once you see it that way, then the next step is to figure out, well, what does happen here? So if I were to multiply this out, I'd get 2 times n, and that 2n would multiply 3n, which would give us 6n squared plus some junk we don't care about, over n squared. And now if we let n go to infinity, we can see 6n squared over 1n squared would go to a limit of 6. So that's your answer for that one. Tougher one, but that's how you do it.